All right, hey Calc folks. Excited to bring you a new lesson today. Today we're going to look at a couple existence theorems. Okay, so we've looked at an existence theorem already. It was called the intermediate value theorem. You know, I talked about, I used like growth as an example. At one point I was this tall. Later on I was this tall, so there must be a point there I was exactly this tall, right? For every k between f of a and f of b, there's a c between a and b, that type of thing, as long as the function was continuous. So we're going to add a couple existence theorems on today, and I think they'll make sense to you. I think they're pretty intuitive. The setup isn't too bad. So let's get started with the first one, Rolle's theorem. Let f be continuous on a closed interval ab and differentiable on an open interval AB. So remember what that word continuous means, okay? It means that we can draw it without lifting the pencil. It's a nice smooth curve. There aren't any points missing. Continuous function. Okay, differentiable, the derivative exists at every point in that open interval. If f of a equals f of b. All right, I got to stop now and I need to start drawing a picture here to make sure I understand what's happening. So and draw some axes. We have some interval AB. Let's say A is right here, and let's say B is right here. Okay. Now it's going to be a continuous and differentiable function on that interval. Okay. I'm not going to draw it yet though because I'm looking at this criteria. If f of A equals f of B, that means they have the same y value. So let's say we're here and we're there. That's f of a and f of b, and they are equal. Okay. Now I can draw my function. And it doesn't specify what has to be true about this function other than the fact it has to be continuous and differentiable. It could look like this. It could look like that. It could look like this. Right? I mean, there's infinitely many ways that this could look, but let's just pick one of them. Okay, let's draw a function maybe that looks like that. All right, so if f of a equals f of b, got it. There is at least one number c in the open interval ab. There is a c between a and b, okay, such that what? Such that f prime of c equals 0. Well, what does it look like for f prime of c to equal 0? The derivative equals 0. The slope at the point is 0. And when we look at my function here, okay, I'd say right there is a point where f prime is equal to 0. There's a horizontal tangent line. That means the c value would be right there. F prime of c equals 0. Okay. So Rolle's theorem guarantees if it's a continuous and differentiable function on the interval AB where f of a equals f of b, there's got to be a point in between on the function where the derivative equals 0. So let's have some fun and see if we can draw some other functions, okay, and see if that still holds true. Okay. How about that function? Is there a point? Is there a c between a of b such that f prime of c equals 0? Yeah, probably right there. How about this one? Is there a c between a and b, okay, such that f prime of c equals 0? And this one I see too. I see right there. I see right there. Okay, notice that the theorem says at least one number. There could be more than one. How about that function? Yeah, every point in AB, it has f prime of c equaling 0. See if I can beat it. I know how I can beat it. Aha. Here there's no c such that f prime of c equals 0. There's nowhere where this function has a derivative equal to 0. Remember this point, okay, kind of looks like a mouse's nose or something looking down. This point, okay, is not differentiable. We did not meet the criteria here of Rolle's theorem. It has to be differentiable on the open interval, so that doesn't work. I didn't beat it. You know, I could try to beat it by doing something like that, but then I didn't meet the continuous part. Any continuous and differentiable function has to have a c and a b such that f prime of c equals 0. Okay. All right, I'm starting here. I've got to end there. There's got to be a point where the slope is 0. Okay. So let's look at an example. Find the two x-intercepts of this function and show that f prime of c equals 0 at some point between the x-intercepts. All right, so let's find the x-intercepts. I can factor this. Plus 3, minus 1. So the x-intercepts are -3 or 1. So when we're drawing our graph here, here's -3. Here's 1. Okay. We've just set our interval, right? Okay. And if you think about our function, this is a quadratic. Is the quadratic continuous? Yeah, it's continuous everywhere. Is it differentiable? It's differentiable everywhere. Okay. Notice these two have the same y values, right? So I'm drawing a quadratic, and we know quite a bit about quadratics. This parabola opens up. So I have to start here and there, and it opens up, right? There's got to be some point where the derivative is equal to 0. So let's set this up here. So let's say this. F of x is a quadratic. So it is continuous on the closed interval -3 and 1 to 1, and differentiable on the open interval -3, 1. So just a quick reminder, endpoints aren't differentiable. Okay, we can only be differentiable on open intervals. Endpoints don't count. All right, now, so let's take a look at this. We said it's continuous on the closed interval, differentiable on the open interval. Now we have to say f of a equals f of b. F of -3 equals f of 1, right? Because they both are equal to 0. So, by Rolle's theorem, okay, so I'm following the line now here, then there is at least one c in the open interval, right? AB, so that's -3, 1, such that f prime of c equals 0. Okay, so we prove there has to be a point in between where the derivative is equal to 0. Kind of blocking this one. Find all values of c on -1, 0 such that f prime of c equals 0. Here's our function, -3x times the square root of x plus 1. Well, can we first prove that there has to be some values of c in this interval such that f prime of c equals 0? So let's take a look at this function. Okay, -3x times the square root of x plus 1. Okay, if we think about the domain on this one, our domain is -1 to infinity. Okay. We know square root functions are continuous and differentiable on their domain except for at that endpoint. All right. Well, yeah. Okay. They're also differentiable there, so we're good. So f of x is continuous on -1, 0. And differentiable on -1, 0. Now, can we check and see what f of -1 and f of 0 really are? f of negative 1 equals, when we substitute a negative 1, what do we get? Negative 3 times negative 1 times the square root of negative 1 plus 1. That's the square root of 0. So we're going to have 3 times 0, which is 0. And, okay, what's the other endpoint? F of 0. Well, when we put in 0, that's negative 3 times 0, which is going to be 0. Okay, so that's good. Okay, and we see, so f of negative 1 equals f of 0. We see that their y values are the same. Therefore, by Rolle's theorem, there must be a c in negative 1, 0 such that f prime of c equals 0. So we prove there has to be one. Now let's see if we can find it. I don't know if that copied or not. Maybe not. Yep. Okay, so now let's see if we can find it. Let's take the derivative. Product rule first, times the derivative of the second, chain rule, plus the second times the derivative of the first. I am going to factor out in x plus 1 to the negative 1/2. That's going to leave me with negative 3 over 2x plus, now when we take the negative 1/2 out of the 1/2, that's going to make it to a first, so x plus 1 times negative 3. Let's move that to the denominator. I have negative 3/2 x minus 3x minus 3. So our derivative is what? 3 is 6/2. Negative 9/2, I believe. Negative 9/2 x minus 3. Oh, excuse me. Sneezes. Just double check this again. Negative 3/2 minus 3. 3 is 6/2. I think that looks good. So let's find out where this derivative is equal to 0. Now, a derivative is, or a fraction is equal to 0 only where the numerator equals 0. Oops, lost my x. Okay, add 3. Multiply by negative 2/9. And we have x equals, let's see, that reduces negative 2/3. Is negative 2/3 in the interval negative 1 to 0? Yes, it is. We knew there had to be one in there, and we just found it. All right. Okay. I want to graph this one just to make sure that we're getting the full visual on these type of problems. Okay, that's what our function looks like. Okay, now you're going to notice that's our interval, negative 1 to 0. They have the same y values. It's continuous and differentiable. So there has to be a point where the derivative is equal to 0. And there it is, negative 2/3. So that's Rolle's theorem. Now we're going to extend this even further to something more useful than Rolle's theorem. It's called the mean value theorem. All right. And when you read the mean value theorem, if f is continuous on the closed interval AB and differentiable on the open interval AB, that starts the same as Rolle's theorem. Then it says there exists a number c in AB such that f prime of c equals what? Okay, so when we compare this to Rolle's theorem, we notice that there's something missing, okay, because they look very similar, right? But there's something missing in the criteria of the mean value theorem that was in Rolle's theorem. And that's the part where f of a equals f of b. So we've removed the requirement that a and b have to have the same y values. Okay. So I'm going to start with my sketch here, and notice I left this part blank because I want to see if we can figure that out together. Okay. So we've got our interval a, b again. But now we've got rid of the requirement that they have the same y value. So let me put f of a right here. And I'm going to put f of b somewhere else. Yeah, let's go there. Now I can draw a continuous and differentiable function. I'll just draw one like that. What do you think our conclusion for this mean value theorem is? The last one was that there's a c between a and b such that f prime of c equals 0. Does this have one? Yes, it does, but does it have to? No, if I drew this function, is there any place where the derivative is equal to 0? No. Okay, let me draw that. I like this. Oh, no. Oh, boy. Here we go. Let me redraw this one. Okay, so what is our conclusion? Well, let's go back to Rolle's theorem. Remember that they had the same y value. And there had to be a spot where the derivative is equal to 0. And I think when I draw in these red lines, it might clue you in as to what the mean value theorem is going to be about. Okay, Rolle's theorem. If their y values are the same, there has to be a spot where the derivative is equal to 0. But when I look at that, a derivative is equal to 0 creates a tangent line that's parallel to the line connecting these 2 points. Okay. In the mean value theorem, if I connect those 2 points with a line, there has to be a c such that the slope at c, I kind of missed there a little bit, is equal to the slope of the line between those 2 points. Here's my c. Right there. Let me put that in red instead. Okay, so we're seeing the slope of the curve is equal to the slope of the line between these 2 points. So what are we going to say here? F prime of c equals what? Well, what's the slope of the line between these 2 points? Well, this is a f of a and b f of b. What's the slope of that line? It's f of b minus f of a over b minus a, right? Slope formula, rise over run. F of b minus f of a over b minus a. And that's it. Why is this called the mean value theorem? Because this is the average slope of the curve on this, right? It's that slope of that secant line, right? So that's what we have. And let's draw some other graphs here as well, just to keep playing around with this idea. Now, last time I had f of a lower than f of b. What if I put f of a up higher and f of b down lower? Okay. And let me draw a function again that goes like that. Well, if I find the slope between these 2 points, is there a c in our interval where the slope of the curve matches the slope of that line? Yeah, it's probably right about there. This is my value of c. Okay. And I can't break this, okay, unless I don't follow the criteria. If it's not continuous or not differentiable, then that's not going to be true. But if it is, it has to be true. Okay. So let's take a look. Yep, last example here. Find all values of c in the open interval -1, 1 that satisfy the mean value theorem. Well, first off, this is a polynomial, right? So let's make that statement here. F of x is a polynomial, so it is continuous on the closed interval -1 to 1 and differentiable on the open interval -1 to 1. Okay? And that's all the criteria that there is, right? So by the, I'm going to abbreviate, mean value theorem, there must be a C in that interval, -1 to 1, such that f prime of C equals, okay, now in Rolle's theorem it was 0, but mean value theorem, it depends on what that slope is. So we actually have to find that. Let's find the slope between our 2 points. Okay, so what are our 2 points? -1 comma, when I substitute -1 in, what do I get? -1 times -1 squared minus -1 minus 2, 0. And when I put in the point 1, well, this is 1 times 1 squared minus 1 minus 2, -2. So what's the slope between these 2 points? -2 minus 0 over 1 minus -1. That's -2 over 2. This has a slope of -1. Okay? So there has to be a C in -1, 1 such that f prime of C equals -1. All right, so let's find it now. Okay, because I asked you to find all the values that this is true. So we need to take our derivative, and actually before that I would distribute the x to make it a little bit easier to differentiate. Our derivative is 3x squared minus 2x, so lost my squared, minus 2. Let's set that equal to 0. And that doesn't factor, so let's go to the quadratic. -b plus or minus square root of b squared minus 4ac over 2a. Let's see, what do we have there? 4 plus 12, 20, 28 over 6. 4 goes into that. That's 2 root 7. Everything there is divisible by 2. So 1 plus or minus the square root of 7 over 3. Now, I'm going to use my calculator because I'm curious if either of these are interval. Maybe both of them are. We don't know. We know there's at least one. So let's type in -1 plus the square root. No, not -1. 1 plus the square root of 7 divided by 2. It's about 1.8. That one's not in our interval. So this negative, this 1 minus the square root of 7. Oh, it's over, hold on. That's over 3, not over 2. Sorry, 0.54. 0.55. No, that's got the negative. Calculator struggles here. They're real. 1 plus the square root of 7 parenthesis divided by 3. There we go. 1.22. Okay, so that's still not in our interval. Now let's do the minus. -0.55. Okay, and that's in our interval, right? So this is the value that satisfies that mean value theorem. And let's check it. Okay, so this one I already have graphed here for us. Okay, so take a look at our curve, and we're going from -1 to 1. So picture that slope. Now, where are we going to have a tangent line that's parallel to that? Probably around in this area. And let's actually plot that point. So to do that, I'm going to type in 1, it was minus the square root of 7 over 3, comma, f of 1 minus the square root of 7 over 3. Well, that doesn't look right, does it? Now what happened? I know what I did. I set this equal to 0. Why did I set it equal to 0? Okay, I was thinking Rolle's theorem here, wasn't I? We don't set our derivative equal to 0 in the mean value theorem. We have to find out where the derivative is equal to -1. Oh my goodness. Sorry for the waste of time here, guys. Back this thing up. Okay. Mean value theorem says there has to be a spot where the derivative is equal to the slope of the line between the 2 points, which we found to be -1. There we go. So let's add 1 to solve this. Does that factor? Oh, come on, pen. This is what I get for wasting time in a video. 3x, x, 1 and a 1. If we do a minus there, write the minus. There we go. And a plus there. Okay, so what do we get here? We get x equals 1 or x equals -1/3. Now, these are our intervals. This is technically, that's one of the endpoints, right? And we're not interested in finding the endpoints. The mean value theorem says in the open interval AB, -1/3 is in there. So, well, look at that. I'll just do that. There is our point. This looks a lot better, guys. Okay. So here is the slope between those 2 points, and right there, the slope of the tangent line is equal to the slope of that other line. All right, that's going to wrap it up. Thanks for watching today. We're going to keep working with this mean value theorem a little bit more in the next days, but that's it for today. We'll see you later.